So now we get to the electron. So we spent the last two videos talking about light. In the very end of the last video, I briefly mentioned that Einstein said, hey, if light can be treated like a wave and a particle, well, maybe we can do the same thing with electrons. Maybe electrons, we normally think of those as particles, but maybe they behave like a wave. And that was a huge step forward. So if you start thinking of electrons as a wave instead of a particle, they behave very differently, and you can apply a whole new set of math to them, new math principles and math equations. So it's Schrodinger who came up with the wave equation to calculate where the electrons might be, to not think of the electrons as a particle, but as a wave. And I know this is mind-blowing, and really quantum mechanics very much is mind-blowing. So stick with me as best you can. This is the point of the unit where Mr. Crone tells you, if you have Mr. Crone, he'll say, we're going to learn the language of electrons. And he says, the last time he checked, you don't learn Spanish in one day. So you're not going to learn the language of electrons maybe in one video. It might take 2 videos, or he'll say it takes 2 days to learn a language. And by the end of 2 days, hopefully you're good at understanding this, or you get the main concepts to be able to do what we're going to ask you to do. At first, it's going to seem really difficult. It's going to seem way over your head, but what we eventually ask you to do tends to be pretty straightforward once you get the gist of it down. So stick with me, absorb as much as you can. You're going to be frustrated at first. It'll all come together in the end, I promise. So the wave equation. Instead of thinking electrons as a specific point, a particle, we think of particles, it's located exactly right here. You can't do that with electrons because they're so small. So the wave equation says, what's the probability of finding an electron? Because we can't ever locate exactly where it's at. It's too small to do. So it becomes a little trickier. So they say, okay, what's the probability of finding it here? What's the probability of finding it over there? So we treat the electrons more as a probability function than as an actual specific spot. Now here's the equation for Schrodinger's wave equation. So write this down, sharpen up on your calculus skills, because we're taking this class to another level. No, I'm just kidding. Don't write this down. You don't need to know this equation, but it is very complicated. That's all you need to know. We're going to simplify it. So here's what this boils down to. Instead of treating the electron as a single point in space, we're going to say, and let me get my pen rolling here, the electron is most likely to be found in this blob. That's what the wave equation says. So this wave equation, what it does is it essentially calculates out 3D maps. Here's our 3D maps that it calculates out. So you can skip all the math and you get to the answers. So it gives us a picture of where the electron is most likely to be. Now we call these shapes orbitals. So you got a lot of terminology to pick up on this unit. An orbital is a 3D region that describes where the electron is most likely to be. Each orbital holds 2 electrons. Now the electron cloud is a combination of all the orbitals. So if you take the shapes in this slide, if you were to pile them all up, so here you got like the z-axis, the x-axis, and the y-axis. Now each shape is pulled out and put on its own set of axes, but if you were to pile them all in onto the same coordinates, they overlap, and they overlap to form what we call the electron cloud. So we used to think of the atom as looking like this. The Bohr model, terrible circles, but you get it. Now we think of the atom as looking like this. So it gets a little bit more complicated, but it explains what we observe better, so it's worth doing. So quantum mechanics, it's the mathematical treatment of where the electrons are found. So again, these are the shapes, the probable locations of the electrons. So now instead of thinking about the Bohr model, see if I can draw a better circle this time. Oh God, no, it's not, but it'll work. Instead of thinking of this as the first energy level, Now we think of this as the first energy level. This might be the second energy level, so it's a sphere. And the weird thing is that there's levels within levels. So this might be the second energy level, and then each of these are also the second energy level. They're just sublevels within that energy level. So that's another trick we're going to have to add to our arsenal of electron counting here. Now quantum numbers. Do not write this table down. This is just there as a graphic, I guess, to the slide. The quantum numbers describe the location of every electron in an atom. So every electron has a unique set of 4 quantum numbers, and it gives the address of an atom. Now, if you take college chem or go into college, you'll use these quantum numbers. We got the principal, the secondary, the magnetic, the spin. We're going to keep all that the same. The symbol, we use N, L, M, and S. And then the rules here get much more complicated. We're going to simplify it. So I just want a disclaimer that we're giving you a simplified version. If you go to college and you say, that's not how Mr. Zeta taught me, they're right, I'm wrong. We're just making it easier right now. Concepts are all the same. We're just designating things with a little bit different numbers. So, to start with, I got an address up here. This is the address of Rocori High School. So this address tells me where this building is located that I'm currently sitting in. So we've got a state. So that tells me generally what state we're in. Now more specifically, what town within that state. Then on what street within that town. And then the very specific number that brings you here. So this address gives me varying levels of specificity, or how specific they are. If I were to just give you, yep, Rocori's in Minnesota, not very specific. If I were to say it's in Cold Spring, Minnesota, that's getting a lot better. If I tell you it's on Fifth Avenue, not North Avenue, now that's really specific. And then the last thing is the number would bring you right here. We do the same thing with electrons. We have 4 quantum numbers. The principal quantum number is the main energy level. Well, I've already told you there's 7 of them in a previous video. That tells me generally what energy the electron has. Within the principal quantum number, or within the energy level, there are sublevels. They have slightly different energies, but we call this the azimuthal or the secondary quantum number. I almost exclusively refer to it as the secondary quantum number. You'll rarely hear me say the azimuthal quantum number. But we designate these as S, P, D, or F. There are 4 sublevels that we work with. The magnetic quantum number. This value depends on what sublevel you're in. If you're in an S sublevel, your M value is always 0. If you're in a P sublevel, you can have any one of these values. A D sublevel, your values can be 1 through 5, 1 through 7 if you're an F sublevel. And then the last one is the spin quantum number. It gives you the spin of the electron. Now it can either be up or down. We say the spin is up or down. So plus 1/2 is an up spin, minus 1/2 is a down spin. Or sometimes you'll just see plus and minus. I tend to use this one. So if I gave you an address here, I said an electron is in the second energy level, it's in a P sublevel, its magnetic quantum number is Y, and it is plus 1/2. That may seem confusing, but it's pretty much the same thing as this. It tells you what energy level, what sublevel, which orbital it's in, and then is it an up or down spin within that orbital. And again, that made 0 sense to you, I'm sure, but it will hopefully shortly. Just know that this is very similar to this. They're both addresses. This is an address in the real world. This is an address. Technically, the electrons are in the real world, but it's so small that we don't really think about it as much. Now, Mr. Crone also has an example. He's going to draw this for you. I tend to use a different example, so write this down. I can do this in my class too if you're excited about the upside down dorm room, but I'll leave this here for you to write down, and Mr. Crone will cover it for you. So what I have here, we have remember the energy level is 1 through 7. What I have here are S, P, D, and F sublevels. An S sublevel looks like a sphere. A P sublevel is shaped like a dumbbell. A D sublevel has all of these funny shapes, and an F sublevel has even goofier shapes. An S sublevel, remember its M value is always 0. A P sublevel can be X, Y, or Z. The reason this can be X, Y, or Z is because this one is oriented on the X-axis, this one's on the Y-axis. Or sorry, this one's on the Z-axis, and this one's on the Y-axis. That's why we call these X, Y, and Z. It shows us which way they're pointing. The reason an S sublevel has a value of 0 is because no matter how you rotate a sphere, it always looks the same. It has one orientation. The D sublevels, we just number them 1, 2, 3, 4, 5. This is where we simplify it. Technically, these are the correct designations, but you do not ever need to know these for general chemistry. And then F, it gets even weirder. You look at those values, we just number these 1, 2, 3, 4, 5, 6, 7. Because there's 7 of them. This is kind of a roadmap that we'll talk about in class. So you can see we've got our energy levels. Energy levels 1, 2, 3, and 4. Now the first energy level only has one sublevel. It has an S sublevel. Second energy level breaks off into 2 sublevels, an S and a P. And then we got an S, P, and D sublevel in the third energy level. Then the fourth energy level breaks off into 4 sublevels. So we got levels within levels here. Now each box on this sheet represents an orbital, and I'm not going to spend a lot of time on this video with this because I want to explain this in class. But just know that this box chart is kind of like a detailed version of this. Instead of the simplified version of energy level 1, 2, and 3, now we know that there's like sub-levels within the energy level. So the second ring has like a sub-level within it. That's what I want you to know for now. And then here's some helpful shortcuts. The N is equal to the number of sub-levels per energy level. N squared is equal to the number of orbitals per E level. And again, don't worry too much about this. This is the number of electrons. Just write this down. Don't worry about understanding it yet. Number of electrons per energy level. Sorry, I can't talk and write at the same time. So number of electrons per energy level. So I'll do an example. This is how many electrons are in the 5th energy level. So remember, N is our energy level. So this is my shortcut for the number of electrons in an energy level. So N equals 5. So the energy level, N equals 5. So I use the equation 2N squared. I put 5 in for N. So 2 times 5 squared is equal to 2 times 25, which is equal to 50. So this shortcut right here tells me that there are 50 electrons in the 5th energy level. If I want to know how many electrons are in the 4th energy level, I would put the number 4 in for N. If I want to know how many electrons are in the 1st energy level, I'd put 1 in for N. So how many different types of sublevels are in energy level 3? So the number of sublevels per energy level, that's this. So N, if I'm working with energy level 3, N equals 3. That's how many sublevels are in the 3rd energy level. I believe I have one more. How many orbitals are in energy level 6? So I use this equation. So N squared, so 6 squared, and my answer is 36. So that is where we will end. We'll practice more on this, and again, if you feel confused, just calm down. We'll continue to work in class, and it will make sense shortly.